Hello everyone, welcome to another class on the course of Quantum Theory of Many-Body Systems in Condensed Matter. My name is Luis Gregorio Dias at the Institute of Physics at the University of São Paulo in Brazil. And in today's class, we're going to talk about electronic transport in the Anderson model. So this is a continuation of the previous lecture where we discussed the transport in the linear response. So we did discuss the conductance, and now we're going to apply that to the case of the Anderson model. So we're going to first start by discussing the Anderson model coupled to two metallic leads, and that changes a little bit from the Anderson model that we discussed, which was connected to a single bath, but we're going to see that the two are essentially equivalent. Then we're going to discuss the current operator, how we define it, and with that, how can we calculate the conductance for the Anderson model through the current operator, essentially a correlation function between current operators, essentially the current correlation function. And at the end, I'm going to mention an application that we're going to develop more in the next lecture, which is how do we apply the Anderson model to a system of a semiconductor quantum dot in the Coulomb blockade regime. And that as I said, we're going to explore this more in the next lecture. Okay, so let's start with the Anderson model coupled to two metallic leads. Okay, so this is the Anderson model, but now coupled to two metallic leads, or two metallic baths if you want. So the different terms here are the following. So we have the impurity Hamiltonian, and we discussed that in the class on the Anderson model. So I'll try to remember to put a link here. There's the impurity Hamiltonian, which is this one. So it's the sum over spins up and down of a epsilon naught, which is the energy of the impurity level, times the number operator for I'm saying the dot here, but this is the impurity, okay? I'm already jumping into thinking of this as a quantum dot, but this is the like impurity, and these are like the D levels. So there's the number operator for the D level or the impurity level, and notice that there's a sum over spin here. This is for a given spin sigma. So the sum will be ND up plus ND down. And the same energy the energy is independent of the spin. And now this is the important term, which is the Coulomb repulsion between the electrons inside the impurity. So if you want to add a second electron or second particle into the impurity, this will cost you this extra energy U. So if ND is 2, so ND up is 1 and ND down is 1, you would get a factor of 2 epsilon 0 from this term, that's the single particle, plus U. So if you want to double occupy the dot, that's the energy that you need, right? You need this extra energy with respect to the case of the single particle. Okay, so the next term in the Hamiltonian is the coupling term. So it allows from electrons from either of the baths. So here I have a bath to the left of the impurity and one bath to the right of the impurity. So this involved is a sum over K, which is the quantum number that labels the states here in this bath. So you might think of K as a momentum if you're thinking this is like a metal and this is like a free Hamiltonian. Like this is the Hamiltonian for the band, right? Like if this would be a free Hamiltonian proportional to K squared, for instance, this could be the momentum. So I'm using the discrete values for K here just for simplicity, but we're going to take the continuum limit later. So there's then this tunneling probability which is essentially an energy, the hopping energy. that is essentially related to the probability of a process for an electron to go from one of the leads into the dot, and there's the Hermitian conjugate, which is the reverse of that. The important thing here is that I have two leads, so I have this index L that is either left or right, and that takes into account that I have two processes, right? One that goes from left to the dot, and one goes from right to the dot, and the other way around. The one that goes from the dot to the left lead and the dot to the right lead. I'm calling them leads, but you can think of them as reservoir. Leads are in a quantum dot language. So notice that this can change the charge state, the number of electrons in the dot, right? The total number is still conserved, like you create one here, you destroy one there, but locally in the dot you might have a situation where you might change the number of electrons. In fact, and this is important here, there might be a second order process where one electron hops from the left lead into the dot, and then it goes from the dot to the right lead. That's the process that we're interested in. Okay. Now notice that the Hamiltonians, the free Hamiltonians for these baths only involve the number of operators on each bath, right, at either left or right for a given spin sigma. So there's three indices here. Case for the state, left is whether L is whether this is left or right, and sigma is the spin. Now this energy here essentially tells me the energies for each state, and implicitly there is a Fermi energy or a chemical potential in here. Okay, why? Well, that's how we sort of take our zero of energy. That's how we did in the Anderson model back then when you had a single lead, and that's essentially what we have here. So you can think that, if you write the Hamiltonian for an electron gas here, and this would have a chemical potential associated with that, and that would be a chemical potential on the left lead, and that would set the energy, the Fermi energy, or at zero temperature, or the chemical potential at finite temperature. And that would be, the energy from which I know whether the n is approximately 1 or n is approximately 0. Okay, so from the occupations of all these K's, I can have a measure of this chemical potential. Now, the important thing here is that I'm going to allow for these chemical potentials to be slightly different from left to right. Very small difference, but I'm going to assume that, say, the chemical potential for the left electrons is a little bit larger, higher than the chemical potential for the right electrons. So the chemical potential is essentially an overall constant value that I add or subtract here to all the levels. Okay. So essentially, I'm shifting the energies from, say, the electrons here at the Fermi energy. The electrons here at the Fermi energy for the right are slightly below than there, and these I'm calling delta mu, which is a difference in chemical potential, and that's going to be our small parameter in linear response when we do it later. So let me just give you an idea of what would be a electron transport process in this system. So for that, if I have this small imbalance, it means that in a situation like this, when the dot level, where the dot is empty and the dot level lies between this chemical potential in the left and the chemical potential in the right, I might be able to favor a process like this, which is a electron is created in a dot in the impurity and destroyed in the left lead. Okay, it is energetically favorable for the electron to do it, because this level is slightly below the energy ore of where this electron was. So yeah, you can think that I create a hole here and create an electron here. And now following up on this process, there might be another process that takes this electron from the dot, so destroys it in the impurity and creates it in the right lead. So what happened here? This might also be a process that is energetically favorable, because now I'm taking an electron from a dot level that is a little bit larger than the chemical potential in the right lead and going from here. So now this cascade, like this two-step process, might be even favorable if the dot level or the impurity level lies in between this window, this very small window. Now, what's going on? What's the net effect of the second order effect? So notice that this is an effect that is second order in a tunneling, so it's t squared. So the net effect is that I transfer one charge from left to one charge from right. So I have a change in charge here, which is negative, and a change in charge here, which is positive. So I gain a charge here. So that means that I have an electric current. Okay, so means that I have electrons flowing that way or holes flowing this way, and I can define an electric current by multiplying the number or the change in number of electrons by the charge, which is minus E. So if you think in terms of electric currents, it would be like a current flowing this way, right? It's the way the holes flow, but the electrons are going this way. Now, so this is the basis of what we're going to start looking at in terms of transport. Notice that this delta mu is small, so it doesn't affect. So I can, in linear response, calculate everything in an equilibrium. That's what we're going to do. So it will depend on the spectral properties of the impurity and the baths here, and we're going to try to calculate the conductance for this case. So yeah, so this is the picture that we have the Anderson model in. So let's look at the current now. Okay, so let's now define the current operator. So the current operator is essentially what I mentioned before. It can be thought as a variation of charge, say in either lead. So I'm going to define the current that leaves or the left lead as the variation in charge at that lead. Okay, so this is the total number of electrons there, sum over k and sum over sigma at lead L, right? And this is written in the Heisenberg picture, so it is time dependent. So if I multiply this by the charge, which is minus E, that gives me the current that essentially is flowing out of lead L. All right. So if ddt is positive, or let's say that ddt is negative, like in the previous example. So when I take ddt out, so ddt is negative, so that this IL will be positive, right? So I have electrons flowing out, so the current is positive because I have holes flowing in. All right. So let's take this as, you know, if the electron leaves, the current is positive. All right. Now I'm also going to define, since I have the total charge has to be conserved, I need for the time derivative of the electrons, the number of electrons in lead L, plus the time derivative of the number of electrons in lead R, or minus them. This should be minus this, okay? So that the total number, the derivative of the total number doesn't change. So let me try to write this here. So what I mean is this. I have NL of t plus NR of t is the total number. Okay? And this should not depend on time. So the total derivative of this, so let's see. The total derivative of this, and let's put here the total derivative here, should be 0. That means that dNL of t should be equals to minus dNR of t. Okay? So what I'm doing here is I'm adding, if I define the current that leaves L as this, and the current that enters R with this minus sign, by the conservation of charge, the total charge cannot change. It means that these two numbers have to be equal, because here I have minus e times dt and L, and here I have minus e times minus dt and R. So these two should be equal, okay? And if they're equal, I can write the conservation of current, and here I'm calling current these two, right? The current that leaves L equals to the current that arrives on R, and that's what I'm calling the current, right? This I here. So this I is, I can write it as this. It can be, say, IR, which is plus a 0, which is L minus alpha IL, any alpha here, okay? This is 0. So, but since IL equals IR, this is also equal to IR plus alpha IL minus alpha IR, so which gives me precisely this expression here. So this is just another way of expressing the current as a alpha plus IL plus a 1 minus alpha over IR. This might seem that I'm doing nothing here, but this, if we choose the alpha here in a special way, this will solve many problems. All right, so let me erase here, and let's try to go back to the slide. So I'll leave you to the assignment that you can express these currents in terms of the creation and destruction operators by essentially writing the Heisenberg equations for these two operators here. And it will turn out that these currents will have this form. It's going to be I times K sum over spin sigma. Then there will be a TL star here, C dagger, KL, CD minus, and this minus is important. It's going to be coming from the minus I. CD dagger, C, KL. So there's a current that leaves L, and the current that arrives in R is very much identical to this one, except that we have a minus I here, minus sign here, okay? So one important thing is that here I'm assuming that these couplings do not depend on K. That makes the calculations easier, so I can take this out of this sum, and that's what we're going to do. Having a dependence on K doesn't change things much qualitatively. Just I'll have to keep that in this sum over K all the way, And well, that's essentially more algebra. So that's the idea you can do in the assignments. And so the important thing here is that I'm now defining a current operator in terms of the creation of destruction operators for electrons in the dot and electrons in the lead. Okay, so now that we define the current operator, we can calculate the current correlation function, or the current susceptibility, which is defined by this Fourier transform of this correlation function, this retarded correlation function. And as we saw in the previous class, and I'll try to put the link here, we can write conductance as the limit of zero frequency of the real part of IE over omega times this. This also can be expressed, right? So if this is a complex function, has real and imaginary parts, this would be minus E over omega times the imaginary part of the current correlation function in frequency domain, which we can in principle calculate, right? We have this written in terms of the operators. We can define this in the Heisenberg picture, and we can calculate this current correlation function. So that's what we're going to do now. It's a rather long calculation, but we can arrive at the following result, where the imaginary part of this object depends on spectral functions, essentially, of the electrons in impurity, and a spectral function in this is the antisymmetric combination of the lead operators that we're going to define here, times at non-zero temperatures, times the Fermi distributions at different frequencies. So let's see how we arrive at this expression. So let's do some calculations in the blackboard. All right, so the first thing I'm going to do is to write the current operator in terms of the antisymmetric combination of lead operators. And by that I mean this. I can define this operator, CKA, this A for antisymmetric, as the following. 1 over TR square plus TL square, okay, times TL times CK left minus TR times CKR. Okay, so I could also define the symmetric combination of these operators. That would be a plus here. So these two is like rotating, in a sense, these operators here to this other basis. And why is this important is because I can, if I choose my alpha here, so I'm choosing alpha as expected value of TR divided by TL square plus TR square. Notice this alpha can be any number, okay? So if I choose alpha to be this way, that leads me to the current to be written as in this form. Sum, well, let's before I do the sum, let me do something. Let me write minus I, okay, there's this, and essentially I'm going to plug IL there, okay, and IR here with alpha choosing being in this, so you can do it yourself, I guess. Right? It's just an algebraic manipulation, and this becomes in this form: square root of TR plus TL square times this sum over K and sigma of TL TR. Right, there's TR is TR star. There's TL here, but so TL TR CKA dagger C sigma minus TL star TR star, sorry, there's a CD sigma here, times CD sigma dagger CKA sigma. Okay, and this I will define as minus I times a T bar number operator of CAD, which is this combination. Okay, CKA dagger CD minus T bar star and AD sigma. So this dagger. Okay, so yeah, so this is an AD dagger. All right, and why am I doing this? Essentially because that simplifies much of the calculation, since the current now can be expressed in terms only of this combination of operators CD sigma dagger. There's a sum in sigma here, so NAD equals of the sum in sigma of over this is AD sigma. Okay, and a sum over K as well, K and sigma, because this is, yeah, this has another index, right? So there's many indices here. There's a KA D sigma, and this is a sum over K and sigma, gives me with A and D. Okay, all right, so only in the current only depends on this combination of operators, so we can, that makes it easier for us to calculate things like in the Heisenberg. So this is the current operator, and in the Heisenberg picture, this would be EIHT I E minus IHT. So what we want to calculate? We want to calculate this commutator, right? So that we can calculate this in time and then take the Fourier transform. So let's see how we do that. Okay, next step. We want to calculate I0 minus, which is IT I0 minus I0 IT. Okay, or you can, so let's see how does this, or if you want, this is going to be the commutator. If I is minus IT and ID, I can write this as this. So I0 is just this operator. I of t, I need the the Heisenberg terms here. So this is be minus I t bar n a d in the Heisenberg picture minus n t bar n a d also in the Heisenberg t picture. Okay, all right. So let's see. This would be then minus t squared, right? Because I have this here. I could calculate, but would be like NAD T and AD 0, right? Coming from this product minus the reverse, so there will be a commutator here. So there's this minus is over all, right? Because comes from this minus I squared. So this term comes from T and T and T. Yeah, this is not absolute value, just T squared. So there will be a T star square as well, coming from this and the A dagger at T and the A dagger at 0 commutator, because there's going to be this minus, right? All right, so yeah, let me put a key here because I have the commutators here. All right, minus what? Minus then this T squared. And now this is absolute, this is just square. This is absolute value squared of what? I have NAD T times, there's the minus, there's going to be a N AD at 0. Okay, commutator, because I have the other one around too. Plus this one and AD dagger at T and here's dagger, sorry, and AD at 0. Commutator, because there's 2 of them. That's it. These are the 4 terms that I have. All right, so let's keep in mind that at the end of the day, what we want to do is to calculate the expected value of this thing, right? That's what enters up there, the expression for the correlation function. Now, if we look at this first 2 terms, it becomes clear that when we calculate the expectation value of this, I should get 0. And why is that? So let's take a look. The point is that this doesn't conserve particles, the product of these 2. So let's to view this. I mean, when I calculate the expected value, I should be always calculating something like that, right? So it's sum over expected values for the operator inside. And in this case, let's take it even at t equals 0, so you don't have to worry about the Hamiltonian, the type evolution. NAD, as I mentioned, would be something with, yeah, this is actually NAD dagger. Okay, NAD is this and AD is CK, CKA, sigma, CD, right? Sigma, and that would be a given time, right? And then I have the other one, CKA, sigma, CD, sigma. So this has to be 0, right? Even if I have at a different time here. Why? Because this doesn't conserve the number of particles. Here I would have something like, this would be like psi, yeah, there would be a minus sign here, but it would be proportional to, yeah, if you want, it would be proportional to CKA dagger square CD sigma square, something like that. Okay, so this has to be 0. So because I'm destroying 2 particles at the impurity, I'm creating 2 at the level at the same K. So the expected value of these 2 terms, the expected value of this one and this one as well, since they involve C operator C or C dagger square, they should be 0. Okay, so we're not going to worry about these 2. So not worrying about these 2. We're going to focus on these 2 here now. Okay. Now that's what we'd like to calculate. So if I come down and write, let me change the color here. If I come down and write this, I should get, yeah, there's this minus sign here, there's this minus sign here, I get a plus sign of T bar, and this is absolute value square of what? Of the commutator of CKAD dagger, CD sigma. Okay, there's a sum over sigma here, and a sum over K as well. K and sigma at a time T. Times CD CKA sigma at time 0. Okay, and this term would be something like the complex conjugate of that, right? So it would be CD CKA sigma at T, commutator with C KA sigma CD at time 0. So that's my current, what this comes down to. And I want to calculate precisely the expected value of these 2 commutators. Okay. Now, that would be something like that, right? I have T bar squared, there's a sum over K sigma, and then I would have something like this, okay? I would have an expected value of something like the CKA CD sigma both at T, right? CD sigma CKA sigma minus the opposite would also be something like CD sigma CKA sigma CK, now CKA sigma, this is all these is CD time T plus the same thing here, right? Something like that. CD sigma CKA sigma CKA CD minus ck cd times cd ckA at time t. All right, so that's what we want to calculate. So I have these expected values for 4 fermionic operators. And now I'm going to use 2 results. One is that if A is H1 plus H2 and H1 and H2 commute, I can write EIH1 plus H2 at time t equals the product H1t H2t. Okay, and the second what happens here is that if this occurs, I can also write something like that. If I have C2 mu, so this is an operator in H2, C2 dagger at time t, C1 a different state nu, C1 nu prime at time t prime, C2 mu prime also at time t prime. I can factor this as this C2 mu at time t, this guy, times C2 mu prime at time t prime. Then, so this is C1 nu at time t. There is a dagger here, C1 nu dagger at time t prime. Okay, so means that when I write 2, it means that the operator is in H2, and then I have the index 1, the operators in index H1. This would be also in an assignment for you to check, but that should, we did something very similar in one of the assignments for when the states were non-interacting. Here I'm arguing that this is a generic statement. Okay? All right, so let's move on. So if this is true, then let's take, for instance, this term here. Then the first 2 terms here. I would have the first 2 terms to be written as, so let's call this 1, 2, and this is 3 and 4. So if this is true, then I can write 1 minus 2 as the expected value of ckA sigma at time t, ckA sigma at time 0, which is this one, times cd sigma at time t, cd sigma times 0. Just remember that, well, both of these are at time t, right? So, yeah, like EHT, just to remember, for you to remember that if I have something like this, this is also equal to AB BT, because I can always put a 1 here, right? So just to remind you. Then, okay, so this is 1, and then minus 2 would be CD sigma times T, CD sigma. Then I'll have CK A sigma times T, CK A sigma at time, no, this is at 0, sorry, this is 0 and this is T. And this is 0 and this is T. Okay. One thing I forgot to mention is the Hamiltonian commutes with the Hamiltonian that I'm writing here has this part on the that depends only on the symmetric combination of the electrons in the leads, and then another part that only depends on the asymmetric part. And these two parts I'm showing that they commute. Okay, that's another part of the assignment. So we're going to have several assignments showing things like that for the Anderson model coupled to two leads. But the one that the antisymmetric combination that appears here decouples, that's a crucial one, right? This combination is not coupled to the impurity. It's essentially free. So this is an important part of our proof. So that's why we can do this decoupling here, because the antisymmetric operators belongs to H2 here, and the D belongs to the impurity. So the impurity and H2 do not commute, or they commute among themselves, and the Hamiltonian itself can be separated as such, right? Okay, so if we do that, I'm going to write now these in terms of Green's functions. Okay, and now I'm going to remind you what the lesser Green's functions, or the greater Green's functions and the lesser Green's functions look like. That's one of, in our class for Green's functions. Again, I'll try to remember to put a link here. But the greater is minus I times the expected, say the greater for A and B, is the expected value for A at T and B dagger, or A dagger if you want. But since here is all diagonal, let's just put this. A is A dagger at 0, and the lesser Green's functions for an operator A is, this is minus I, okay, minus I, and the other one is plus I. Plus I, expected value of, again, this is not too good, let's put it A, is the other way around, A0, AT. So, with this in mind, I can write 1 minus 2 as the dagger. So there's going to be a plus I times minus I, which gives plus 1. So this would be the lesser Green's functions related to the operator C, K, A sigma, okay, at 0 T. Okay, now this is important. This is the Green's functions at T0, okay, T0. So T, that's the one that has the time dependence on the non-Dagger operator is what sets t. Okay, so this is 0t, not t0, while this one is going to be t0, right? And this is going to be a greater of d sigma t0 minus this is Dagger 0, so this is be a lesser Green's functions as well of the d operator, but this is going to be t0, and this is going to be a greater Green's functions of the Ka sigma operator, at 0t. Okay. Yeah, so this is how the greater and lesser Green's functions are defined. Now 3 and 4, 3 minus 4, which is these other combination here, I can also do the same trick, rewrite them in terms of Green's functions. So those would be the lesser Green's functions of the d sigma operator at 0t, and the greater Green's functions of the Ka sigma operator at t0, minus the lesser operator of the Ka sigma at t0 times the greater Green's functions of d sigma at 0t. Okay. So what have I done here? I essentially now wrote my expected value of this commutator in terms of lesser and greater Green's functions. So I'm at this stage here. Now what I need to do now is to write my Fourier transform. So this slide is already very crowded, so let's go to a new slide. And now I just realized that I actually wrote over the edge of your screen. So I'm gonna try to write what you might have missed, just so that, so here you're probably seeing this G greater, I'm gonna write it down here too, G greater dt sigma 0t, okay? Let me erase this thing, and this part you cannot see anyway. This is GKA sigma at 0t as well, okay? So let me erase this. And of course you have 0t, I'm sorry. What else? Up here, there should be a C, this guy is C1 new dagger of T prime. Okay, that's how we close here. So yeah, all right. And yeah, maybe I went overboard here a little bit. This should be okay. This is a T, okay, so that if you're taking notes, this should be a T. Okay, sorry about that. So I'll try to keep that in mind in the future. So, but let's go to a cleaner blackboard now. So to summarize, we were able to express here the commutator of these current operators in t and 0 as the sum over these products of lesser and greater Green's functions involving the operators, this creation and the structure operators for Ka sigma and D sigma. So what do we do with that? Essentially what we want to calculate is this Fourier transform, and at the end we want to take the imaginary part of this. Alright? So the first thing we'd like to know is how do we take this imaginary part. So let's take a look at this. I'm gonna write real quick and pause the video, and you're gonna see the expression already. Okay, so this is the imaginary part that we want to calculate, right? So 1 over 2i of this minus this conjugate. Notice this is just conjugate. This is a number, so this is not dagger. Okay, so I'd like to have a expression to calculate the conjugate of these Green's functions, right? I know how to calculate the conjugate of this, the minus I, but what happens to the conjugate of these Green's functions? So let's go a little bit below, and let me write what would be the conjugate of, say, a lesser or a greater Green's functions for a given operator D. Okay, here it is. So what I wrote here, let's focus on this part first. I wrote the definitions for the greater and lesser Green's functions. There is a mu missing here. So let's put this real quick. But this g mu at t0 minus I, expected value of c mu at t, c mu dagger at 0, and vice versa. And I also put here the definition for the time evolution of the operators in the Heisenberg picture. There's this EIHT, C mu, E minus IHT. So these are all definitions. Now I want you to notice this. Okay, if I take the conjugate, not the dagger, the conjugate of C mu at t, what do I get? I get the only thing that I have to do is to change I to minus I. So I change I to minus I here, etc. And what I get at the end is simply this, minus t, CV, E minus I, H minus t. So this is C nu at minus t. Okay? All right. So let's go. So we know how to take complex conjugate, not dagger. So let's take the complex conjugate of this guy then, C greater. If I take the complex conjugate, of course, this I will change sign. So that's what I have here. Okay. Then I'll have the complex conjugate of what's inside here. And as I just mentioned, the action of taking the complex conjugate on the operator in the Heisenberg picture, the time dependence, is just to change the sign of time. Notice that I'm not taking the dagger here, so this is just a number. So what I'm doing is I'm just keeping C and C daggers they were. The only thing that changes is that this is now at minus t. This continues to be at 0, right? Because this is 0. Now this is of course a trace, or this is a translation invariant in time, but you can see as a trace, and the trick here is to write this in terms of, instead of minus t here, put a 0 and then a t here. Okay, how do I do that? Well, e to the minus ih here, e to the plus IHT here, right, this minus t, I can shuffle the operators inside the trace in a cyclic way. These two commute, and then I can bring this one, the I minus HT here, from here to here, right? And then this becomes C dagger at t. So all that is changed is that the order of which was before t0 becomes now 0t. Remember, this is the time argument for the destruction operator, and this minus sign here. Okay, so that's all that I get when I do G greater T0 complex. And the same for G lesser T0 complex is just minus G nu lesser 0t. Okay, that's the result that I want you to fix. Okay, now I'm going to continue and try to write this guy and see what we get, how we get the imaginary part, trying to do the subtraction. So yeah, I'm going to write right here in just a second. So I copy and paste what I had before from up there. Okay, so that's the commutator. And notice that I can write from this property, if this is a complex number, let's call it Z1. Oops. Z1. G lesser Ka sigma 0t, GD T 0 greater. And here I have the same thing, except that instead of 0t I have T0, and I have, instead of T0 I have 0t here. So this, each one of these is minus the other one complex conjugate. So if this is a number Z1, this is Z1 star, same thing here. See, if this is a number Z2, 0t, T0, got a minus this star, T0, 0t, another minus Z star, the two minus cancel, but I still have something like that. So this is Z2, this is Z2 star. Okay? Now things are getting more interesting, because here I have Z1 minus Z1 star, which is the 2i times the imaginary part of Z1. And here I have Z2 minus Z2 star, which is 2i times the imaginary part of Z2. Okay, if I continue now, this is a purely imaginary number. Okay, that's the whole point here. And let's put this into the integral and try to take the Fourier transform and see what we get now. So here it is. I wrote the chi, the retarded, now in terms of these Z1s and Z2s. Notice that I had a I there from the definition, and I'm taking only for t larger than 0, so this goes from 0 to infinity. There's this minus I here that I'm combining with this plus I here. I have plus 2. Have these sums of the imaginary parts, and I have the exponential. So everything here is real except for the exponential. Now let's take the conjugate. So here the only thing that changes is in the exponential, right? So I could then think of a Fourier transform in minus t. So what happens if I wanted to do this change of variables, right, from t to minus t? Well, I would definitely get let's do this now real quick so that you have a flavor. So t prime equals minus t. So here, first, the integral would go from minus infinity, from 0, say, to minus infinity, okay? Now, there will be a minus t prime here. Here, there would be a plus t prime, okay? Let's keep in mind this minus 1 here. But this minus 1 would cancel with a minus 1 that comes from this. Why? Well, if g lesser or greater, either one, of minus t and 0 equals 0 and t, and we showed that a little bit above, right? If we just go from t 0t to t0 is the same, right? That means that the imaginary, this z1 calculated minus t equals its complex conjugate at t, just by definition of z1, right? Meaning that the imaginary part will change sign. So the minus 1 that comes from here with a minus 1 that comes from dt gives me the plus sign that I want. So the complex conjugate is exactly this, with the integral going from 0 to minus infinity. Now I could do this, right? Now I get a minus sign, and this is going to be important. Let's take a minus sign here going from minus infinity to 0. All right? And then if I add, let's put a minus here, plus here, and now if I add these two, I get the imaginary part of chi 1r. I get the full integral over t with no theta, so this is not like a retarded function, but I'll get the full integral from minus infinity to infinity. So this would be the Fourier transform of whatever is in here, which is a real number. Okay, so let's see what you get in another slide. Okay, so I just copied the results that we had before, and we want to add those two, right, to get the imaginary part of chi ir. Just remind you what z1 and z2 are. So the imaginary part of z1 is this, g lesser, ki sigma, gd greater, and so on. Here I only changed from 0 to t to minus t to 0. Remember, we can always do that. Can always do this, right? 0 to t and write it to minus t to 0. I'm doing that for a reason. We're going to use a property of a Fourier transform, but let's see what you get when we add these two. Okay, so when we add these two, I'm going to stop here. There is a 1 over 2i here. Okay, essentially that's what I'm essentially have a 1 over 2i here. There's going to be these two t bar absolute value squared. So 1 over 2i squared is minus 1 over 4 times these two t bar squared. I get minus t bar squared over 2. And here I have kind of a Fourier transform. dt e over e omega t, sum over k sigma, the sum of these two imaginary parts. Okay, now let's keep on going, and now we're going to see the time dependence of this, which is encoded in these Green's functions here. And first I'm going to use this property. If I have the integral over dt e omega of two functions, ft and g minus t, this can be written as a integral over d omega prime over 2 pi of, say, the Fourier transform of g of omega prime times f of omega plus omega prime, where this omega is this one. This you can prove that by inserting, say, a delta function here and taking the Fourier transforms. Okay, same thing if I now choose to have minus t in f and plus t in g, then f will be omega prime minus omega, and g will be of omega prime. So this is a property of the Fourier transform, and I'm going to use it here, right? Because I have minus t, t, t minus t. So when I do that, notice everything that is GD, I'm going to choose it to be this G function here. While everything that is Ka sigma, I'm going to be the F, which is going to have omega plus omega prime or omega prime minus omega. All right? Once I do that, I can write my imaginary part of chi of omega as an integral in omega prime. There's going to be a t bar here, t bar square. And then I'll have gt omega prime, say like this one is greater, so it came from g1, z1, right? T and minus t. 1 is going to be omega plus omega prime. The other is going to be omega minus omega prime. So there's the lesser Ka. Same thing for z2. Okay? So we're almost there. So we already have the imaginary part of chi IIR in omega. Is going to be this integral in omega here. But we can do more. We can express these greater and lesser Green functions in terms of things that we can calculate, say the spectral functions. And for that we use the fluctuation dissipation theorem. Okay, which is this G lesser, that's the one that we saw in class. G lesser of mu is 2 pi I, the Fermi distribution, times the spectral function, the minus 1 over p of the imaginary part of the retarded Green functions associated with this operator C nu. Now you can write one for the greater Green functions as well. It's going to be minus 2 pi I 1 minus nf of omega, the spectral function of A nu. And with that we arrive at the result that we want. There's going to be a 2 pi here. The i's are going to cancel. I mean, they're going to become a minus 1. And I'll have the 1 minus nf here, right? You have to do the algebra here. But at the end of the day, all that I'm left with is with spectral functions either resulting from the impurity electron, just to remind what these guys are. AD of omega is minus 1 over pi, the imaginary part of the retarded Green functions of the dot, which we already calculated at least in mean field, and you can calculate with, say, equations of motion as well. Okay. So this is the Green functions here. Okay, so this is something that we know how to, at least how to calculate, either using equations of motions or mean field, right? But we're gonna next class we're gonna see a more robust method to calculate the spectral function. So this is the spectral function. So this was a long derivation, but we did it. Let's go back to the slide. All right, so this is the imaginary part of the current correlation function, and we have this, we can express the conductance in terms of these guys. So let's see how we do it. So we're almost there, and let's now express the conductance in terms of the spectral function for the impurity operators with this derivative of the Fermi distribution with the energy of the band electrons. And notice that aka sigma disappeared here. So let's see how we arrive at this expression, starting from the one that we had in the previous slide. So let's take a quick look at the blackboard. This is going to be quick now. Okay, so we have everything essentially here. So we know the expression for the imaginary part of the correlation function. has all these terms here, aka sigma, these funny combinations of the Fermi function as a function of these omega prime, and we have this integral in omega prime. All right, so we want to take the limit, omega going to 0 here, okay? So the first thing we want to notice is this. Notice this, there's this difference nf omega prime plus omega minus nf omega prime, and there's going to be a 1 over omega multiplying here. So when we have this, this will become something like that. And we want to take the limit of omega going to 0. So in this limit is like omega plus a delta omega prime, something very small, minus nf omega prime, and the something very small is here. So it's like the derivative of the Fermi function with respect with omega prime. So in both of these cases, that's what we get. Okay, now, except that this is minus the derivative, so there is a minus sign here, which will make up for this minus sign. There might be a factor of 2 here missing, okay? Yeah, I think there's a factor of 2 that we forgot in the previous slide. So now what we do with the spectral function aka, remember this is, what is this? Aka sigma is minus 1 over pi, the imaginary part of the retarded Green's functions ka sigma, which is minus 1 over pi, the imaginary part of this guy, CKA dagger. Okay? Well, what's the Hamiltonian for this guy? We know that the Hamiltonian decouples from the impurity and the other terms. So this is, it commutes with the total Hamiltonian, right? So that's what, and you're going to prove that in an assignment. So if that is true, then we know what's the Green's functions for that is just 1 over sum over omega 1 over omega minus epsilon k. This is omega plus this I theta. So if we take the limit theta, that the imaginary part of that is going to be this, just the sum of delta functions there. Just we had an assignment where we showed precisely this, right? In the limit of theta going to 0, we get the delta function. So this is going to be a delta, this is omega prime, it's going to be just delta of a sum of delta of omega prime and minus ak. That's either for just a sum of k. That's for either spin, right? Now, if I plug this sum of delta functions here, what I'm left with is omega prime equals to epsilon k, which there will be a sum over k here somewhere. There should be a sum over k, and probably a factor of 2 here as well to account for this. And then whatever is omega prime becomes epsilon k in the integral, and you're left with the expression that we wanted. Okay. So this is 2 pi t square e square sum over the spectral function of the dot, but calculated at the function epsilon k of the electrons in the leads, right? So there's a sum over k, and now let's take the continuum limit for that. So the final result here is that when we take the continuum limit, we substitute the sum over k, not the sum over sigma, just the sum over k, as an integral in energy times the density of states at that energy. Okay, this is an important factor that we mentioned in the electron gas, how this comes about, but this is important. So that here I would need that there's going to be, this will become an integral with a density of states, and I define this function, which is essentially I can this gamma function, okay, which is 2 pi times the absolute value of the coupling, either L or R, TR or TL, squared times the density of states in the leads. And here I'm assuming that the density of states in both leads is the same. They're both metals with the same density of states. And you can assume that they're different. It's not going to change much because everything that is important is what happens near the Fermi energy. So with that, I can also define this gamma bar, which is going to be gamma left, gamma right, square root of gamma left square plus gamma right square. And you can show that this is essentially gamma bar is 2 pi T bar times the density of states here. Okay. So with that, I have the continuous version of this at finite temperature, and this is sometimes called the Landauer-Büttinger formula for the Anderson model, sometimes the Meir-Wingreen formula, coming from a very famous paper by Meir-Wingreen and Yuval Meir in the late 90s. And so this is what we're going to use to calculate the conductance for a system where I have an impurity and I should know how to calculate the spectral function, and this will give me not only the conductance but also a temperature dependence, because there's a temperature hidden in here. And we're going to discuss this more in the next class. So before we go, let me just give you a hint of what we're going to see in the next class. So the application we're going to discuss in the next class is quantum dots in Coulomb blockade regime. Let me mention really briefly why we studied all these equations to get a conductance expression for that. So there is a system where you have a region where electrons are confined. So you have a quantized levels of electrons in this region. So you have something like that. Plus you have charging energy. So you do have a charging energy. So a cost in energy to add an electron into this so-called quantum dot. And in addition, it is coupled to leads, just as we have in here. So process of single electrons going into the dot and out are very much dominant in the so-called Coulomb blockade regime. Coulomb blockade is precisely this situation when you prevent electrons from going into the dot because of discharging energy. And this has been realized in nanostructures. Notice the dot is right in there. So this is 1 micron. So the dot is a few, perhaps 100 nanometers across. And this is kind of an old quantum dot arrangement from 2000. The lithography has improved a lot over the years. But this is precisely the kind of system we're going to see, and you can actually measure the conductance from source to drain, and it's going to match very much the expression that we derived in this class. Okay, so I'll see you in next class, and we're going to discuss not only the transport in the Coulomb blockade regime, but also the Kondo effect. See you then.